Hey Thunder Bay, it's Dave from Science North. I know we can't be together for this winter fun day, but come on with me and we're gonna have fun in the snow anyway. Grab your kits and let's go! So we've all made baking soda and vinegar volcanoes before in our backyards. I'm gonna do something like that, but a little bit bigger, a little bit hotter, and a lot more dangerous. The first step we're gonna do is to bury this contraption, which is a bit of pipe attached to a chamber. Kind of like a real volcano, you got a magma chamber down below, and you have the volcano, which hopefully will erupt. Unlike a real volcano, we're going to use a chemical reaction to make this one go off. Real volcano is just dependent upon heat and pressure to explode. This one, we generate the heat and pressure by having a chemical reaction with a chemical called hydrogen peroxide, which I have here. I'm going to pour that down the vent of the volcano. I already have a bit in there. Now, hydrogen peroxide is a chemical that's unstable. It wants to fly apart because it's basically water with an extra oxygen molecule stuck on the side of it. And so it wants to burst apart into water and oxygen. And when that happens, it generates a whole lot of oxygen and also heat, which boils the water into steam, which should make our volcano erupt impressively. But in order to see it the best, I'm gonna add some soap. The soap is gonna act as an indicator. Now, an indicator in chemistry is something that sort of shows you the reaction is happening. In this case, the indicator is regular good old Blue Dawn soap. We're gonna throw some in the bottom there. And this Dawn soap indicator is going to trap some of the oxygen and steam as it's produced inside of bubbles. So we'll be able to see it as it comes out of our volcano and flows onto the cinder cone. But to make things a little more dramatic and to make it so we can see everything very, very well, I'm going to add a little bit of blue dye. Because who doesn't love blue dye, right? We'll just drip drop a little bit into our bottom there. Great! Now all we need to do is wait. But we'll be waiting for a very, very long time for two reasons. One, this reaction doesn't happen very quickly on its own. It's unstable, and they do fly apart, but it happens very, very slowly. Also, we're outside in the cold, and the snow is cold, so chemical reactions happen very, very slowly when they get cold. So we have to add a little more in the form of what's called a catalyst. Now, a catalyst is a special kind of chemical. A chemical that makes the reaction happen a whole lot faster without being used up itself. The catalyst we're going to use for this is a solution of potassium iodide. Now, potassium iodide, when it hits hydrogen peroxide, makes the hydrogen peroxide basically explode into water and oxygen. And then it hits another molecule of hydrogen peroxide, which also bursts off into water and oxygen over and over and over again until you have a volcano. Now remember, it is cold. So this is going to start very slowly until we've had a chance to develop enough heat to make everything speed along. So, count it with me. We're going to go from 10 and make our volcano erupt in a way that a baking soda and vinegar volcano definitely won't. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. I'm going to actually add a bunch more there. Now the reaction is happening. The potassium and iodide are slowly cracking apart the hydrogen peroxide. We're having bubbles that are being formed. You can see that our cinder cone is starting to smoke, and there we have an eruption! Oh, now the magma has turned to lava and is flowing down the sides of the volcano. Now, of course, in the real world, this is liquid rock, and when the liquid rock begins to cool, it would then begin to form solid rock around the outside of the volcano, forming the cinder cone, making the volcano higher and higher and higher. Of course, our lava is not real lava, it's foam. And so when it begins to cool, it will just stop. But still, this is elephant's toothpaste in snow volcano form. Now, not all volcanoes in the universe are necessarily powered by heat and rock. In fact, on some other planets in the solar system, there are volcanoes that are actually powered by ice. They're called cryovolcanoes, where you have heat and they send out jets of water and ice up into the atmosphere around the planets. They're pretty impressive, but I like the ones on Earth because they're pretty hot, just like this one here. So you see, the hotter it gets, the faster the reaction goes. And so our volcano is starting to get really impressive. So So now it's time to make some snow. So I'm gonna pour some hot water into a thing, look around me, and then throw it into the air and make a mess. See, the thing is, this water is not nearly hot enough, and also the air outside is not nearly cold enough. So we don't, the reason the thing that you see on YouTube works is you have super hot water going into super cold dry air, which causes all the water to boil off immediately and giving you a little bit of vapor and snow all around you, and not just a whole lot of, well, what's basically rain. So we're gonna make a different kind of snow. Come with me. So the kind of snow we're making is not real snow. It's sodium polyacrylate. Now we're not going to chemically synthesize sodium polyacrylate because that would take a very long time, a lab, and a lot of equipment we don't have. So we have sodium polyacrylate. What we're going to do is we're going to hydrate it. So I'm going to pour some into my Erlenmeyer flask here. Down to the bottom, and ta-da! Not impressive, really, but that's okay. So the thing about sodium polyacrylate is it's what's called a super absorbent polymer. So you have a whole bunch of tiny little molecules that are kind of stuck together, and when you add water to these molecules, the water goes in and it kind of sticks all around the outside of each and every molecule, getting bound to it very tightly, which means that the polymer can absorb way more than its weight in water by a factor of many times. Let me show you. Got a sodium polyacrylate, which is just a powder right now, just coating the bottom of this Erlenmeyer flask. And if you add a bit of water, just like so, the water is instantly absorbed. And the more water you add, the sodium polyacrylate just keeps absorbing and absorbing and absorbing, making it look like the snow is appearing from almost nowhere. Now this stuff is found not just here, but also inside the diapers of babies. Have you ever wondered why a baby can wet itself and doesn't go everywhere? Most diapers have this stuff on the inside layer of disposable diapers that help grab it and hold onto things. It's also, interestingly enough, used in farming in some places of the world. Because it holds that moisture and sucks it up and holds it tight, that means that some farmers in some parts of the world add stuff like this, and this indeed, to the soil to make it both a little bit lighter, fluffier, and hold moisture a little bit better. So that's sodium polyacrylate, and it's kind of neat. I've got some salt. I'm gonna pour it into the sodium polyacrylate, and we'll see what dry salt does to what looks like dry sodium polyacrylate. Now remember, this isn't actually dry, it's just swollen, so it's absorbed a whole lot. All right, so this is gonna take a little bit of time, so we'll speed this up while we watch this happen. So you can see it's starting to get sloppy and wet, and so it's getting sloppier and sloppier and less fluffy, and so now it's not really snow anymore, it's turned into pretty much slush. So again, what happened there is when I added water to it, the water went in and bound to the outside of each of the sodium polyacrylate molecules, and it threw the sodium off. So the sodium was just sort of sitting around, and the water took up the space where they used to be. But adding a whole lot of salt, which is sodium chloride, the sodium overwhelmed the water, knocked it off of the polyacrylate, and turned the whole thing back into swishy slush. So for this next science demonstration, all you need is some paint, some water, a bucket, a rope, and a hole, which has to be inside the bucket. We're gonna use this to make a clock. You see, a clock is just something that keeps time, that does something regularly, over and over and over again. And in this case, our clock is going to be made of a pendulum. So a pendulum is basically a weight on the end of a long rope which swings back and forth. So the thing is, pendulums, when they swing, take the exact same amount of time to make one complete swing, no matter if you drop it from way up here or just barely off the bottom of the swing. Which is kind of weird to think about. But we're gonna use this to make a clock and art at the same time. So, Make sure the hole's right in the exact center of your bucket, otherwise this won't work. Also make sure the rope is tied directly on the center of the handle so the whole thing swings exactly back and forth. With that done, all you have to do is add the paint. I'm going to add about, let's say, 50 milliliters of paint into the bottom. And I'm going to match that with about an equal amount of water. The reason we're adding the water is because paint on its own is usually thick, so that it sticks to things. The problem with thick paint is that it won't drip through the hole and make a nice stream to give us the art effect we're going to want to see. So I'm going to add the water. We'll mix it up. Hope the stream comes through nicely. There we go, and a little more. There we go, and we have a nice steady stream. Let it go. Now, as this pendulum goes back and forth, if we were to watch this happen over the course of an entire day, what we'd actually see is that this line would slowly twist around and make a giant circle. Now, we're not going to stay out here for that long. So instead, we're going to speed things up and just make art that look kind of cool. I'm going to add a little more water to make ours, and I'm going to give it a bit of a spin. And then all we're going to do is sit back and let the pendulum make our art. Not only is the pendulum cool, it's also helping us to keep time. One of my favorite things to do going outside is to watch rocket launches. Although I've never actually watched a rocket launch. I'm sure I would love to if I ever could. So what we're going to do now is watch a rocket launch. Before we do that, let's talk about rockets. So rockets are propelled upwards basically by a whole lot of wind, which doesn't sound right, but it is technically true. So when you have an explosion happening behind the rocket, you have a whole lot of hydrocarbon fuels, and sometimes hydrogen and oxygen, and sometimes some crazy nitrogen compounds, all combusting. What's happening is they're making a whole lot of heat, a whole lot of light, and some byproducts in terms of gases. And hot gases are really big. They take up a lot of space. And so they want to expand. And as they expand, then they're inside the rocket's interior. And so the only way to go is to go downwards. The gases go downwards, they're expanding, so they also push the rocket up. Newton's laws. Now, let's watch that. And the thing about a rocket is that they give off a lot of heat. So watching a rocket launch between our eyes and, say, a thermal camera, you'll be able to see things very differently. Too bad we don't have one of those, right? Except we do! So this thermal camera is changing the infrared radiation that my body's giving off into a form of light that you can see. We're gonna do this, and we're gonna launch some rockets. Not real rockets, they wouldn't let me do that. Something about, it being dangerous. We have these. So they're pop bottles with fins on the back, but they're also going to be launched into the air, powered by air and a little bit of liquid fuel. Let me show you how it works. I've got right down here some hot water. Why hot water? Well, I don't need hot water, but it makes it look better than the thermal camera. So I'm going to fill one of them. We're going to use a Pepsi bottle here. Is going to be hot water. Oh, that water's a little too hot. I'm going to cool it down with a little bit of the cold water. There we go. Excellent. All right, so we've got the hot water in one. I have cold water in the other. What you're probably noticing on thermal camera is the two look extremely different. The hot water giving off infrared radiation by the pound, not literally, but shows up as bright red, whereas this goes up as dark blue, maybe even purple or black. All right, so we're now going to launch them into the air, not by throwing them. Instead, we're going to add a whole bunch of air. We're going to pump it into the container. Now, the container is going to be sealed with a plug at the bottom. what's going to happen is the pressure will then build up inside as more and more air is added. The same way for a rear rocket, chemical reactions make extra gases. So those gases get built up and pushed out. In this case, our gas is going to build up till it pushes out. And when it pushes out, it's going to push the water out as well, which will launch it high into the air. Enough talking, let's start doing. First things first, I'm going to add a little bit of color. Because, why? It makes things look better. There we go. And a little bit over here as well. There we go. All right, we have our hot water. We have our cold water. We have our rockets, and we're gonna launch the hot one first. They should fly pretty much the same. In fact, the hot one might fly not quite as well. So I'll just seal up the bottle, like so. We'll launch it just like that. And now we'll add a bit of air. So notice how the air goes into the bottom of the boat. Not too shabby. Hope that showed up on the thermal camera. Next, we're gonna add the cold water. Same thing. Sealing it up just thusly. Excellent. Throwing it on like so, and we're gonna add some air. So as the air goes in, the pressure builds, and then the only way for the pressure to go out is through the bottom by releasing the plug! I can't even see it! There it is! Best launch yet! Fantastic! So it's always good to be outside. The problem is, in the wintertime, you got the sun, which is wonderful when it comes out, but when you're outside skiing, snowshoeing, walking, hiking, or doing anything, you can actually get in a bit of trouble. You see, the sun bounces off of things, and it bounces off of snow really, really well. So the sunlight, including the ultraviolet radiation which the sun produces, bounces off the snow and gets in your face. And if you're outside for a long time, your face is getting a double dose, both the UV from the sun and the UV reflected off the snow, so you can actually get a sunburn in the middle of winter. And have you ever noticed when you're outside and the sun's really bright, you have to squint to feel comfortable and to see anything at all? Well, there's a very good reason behind that. Our eyes protect themselves. So if there's too much ultraviolet radiation going into our eyes sense that in the form of bright light, and so they narrow our pupils. They make our pupils smaller and smaller, so that there's just little pinpricks with only a bit of light going in. The problem is, if you have a double dose from the sun and then bouncing off the snow, it can often be too much. And so we need to help things along. And what better way to do that than with a very, very old technology? We're gonna make some snow goggles. Now, first things first, if you have sunglasses, you should probably use those, because sunglasses, they don't just narrow your vision and make it so less light gets through. Sunglasses that have a protective coating called UV coating, they block all the sun's UV radiation going into your eyes, and so they're way better. They keep your eyes healthier, and they let you see a lot better than what we're gonna make right now. But in a pinch, if you don't have any sunglasses, follow me. So these snow goggles are super handy. You're gonna wanna cut what looks kind of like a mask out of a sheet of heavy cardstock, which is what I have here. Imagine you're trying to make a superhero mask, but don't have a whole lot of time. Well, that's what we're making here. Next, you're gonna cut some slits right down the middle where your eyes are gonna go. Just like so. If you're following along at home, the slits don't have to be perfect. They just have to be small. So the purpose of the slits is to not let much light get through and into your eyes, so that you don't get as much UV radiation into your eyes, so you're able to see. Now, if you were to go outside and just keep doing things in the bright, bright sunlight, you can end up with something called snow blindness, which is basically like a sunburn in the back of your eye. which is not a good thing to have. Sunburns alone are not a good thing, but burning the back of your eyes, no thank you. So there we go. We've got our snow goggles. 2 slits, just like so. You're going to want to make a hole on either side for the string. Got 1, and I got 2. Put your string through the holes, and there we go. You got a pair of snow goggles. The kind of things that our great-great-grandparents wore all the time when going out into the snow, they wanted to avoid getting sunburns to the back of their eyes. So animals don't have to depend just upon fur coats to stay warm. There are a lot of other ways to do it too, particularly if you consider that birds don't have fur and so they'd be out of luck. Their feathers are nice and fluffy as well and trap a lot of air, keeping them warm in the winter as well. But different animals have different ways of dealing with the cold. Cold-blooded animals, or ectotherms, things like snakes and turtles and all those frogs and other amphibians, they deal with the cold by basically slowing down. Turtles are my favorite because they dive down into a pond, dig themselves down into the muck, which isn't going to freeze, and then slow their bodies down until basically they're not in suspended animation, but they kind of are. Some types of turtles also pump water in and out of their, well, out of their butt. It's how they breathe, how they get oxygen, but they do it very, very slowly. And that's because their bodies are so slow, they don't need much oxygen, and so they can survive the winter down in that layer of muck that doesn't freeze. They move so little that things like painted turtles actually begin to build up too much acid in their blood, and so their skeleton starts to dissolve. True story. It doesn't dissolve away, but it does dissolve a little bit, which is pretty neat. Other behaviors have things like clumping together. You'll have herds that pack together tightly to help keep the animals on the inside warm, and as the ones on the outside get a little bit cold, and they can then shuffle in and shuffle out. Things like bees will actually just vibrate. They buzz in the winter. That buzzing is super handy because that vibration makes a bit of heat, and that heat keeps the colony warm. And, well, even us, our bodies have a behavior that keeps us warm. And as you can see, I'm starting to shake. I'm not actually cold enough to shake or to shiver, but that shivering motion, that movement of our muscles makes energy, uses energy, it makes heat, and helps to keep us warm. Animals can also get something called hypothermia, which is basically when an animal loses far too much heat, and so their body begins to sort of shut down. It can happen to people very, very easily if they go out into very, very cold winter environments without wearing the right kind of clothes, because let's face it, our bodies are not adapted to deep, deep winter weather. But my personal favorite are animals that adapt to the cold by doing something kind of strange. See all that snow around me? Yes, it is cold, but snow also is made of a whole lot of crystals, and those crystals trap a lot of air pockets in between. And air is a great insulator. So if you have an animal that has enough fur feathers on the outside that they don't let a ton of heat away from their body to start with, if they go into the snow, well, that snow will act as a giant insulator and keep them from getting any more cold. So strangely enough, things like ruffed grouse, when they get cold, they look at the snow, they see that the sun is going down like it is now, take a run, and jump into it. Thanks for watching, Thunder Bay. Make sure to stay warm.